So in today's lecture, we'll be moving on to the next topic, which is artificial neural networks. So artificial neural networks is also a part of soft computing. It also comes under soft computing, right? So basically, the entire course we can divide into three parts. The first one, what we have discussed is fuzzy logic, and then we have discussed about genetic algorithm. MOOPs were also part of multi-objective optimization problem. That is actually a part of genetic algorithm. And the third category what we are going to discuss is artificial neural networks. We are discussing the course soft computing broadly under these three headings: fuzzy logic, artificial neural networks, and genetic algorithm. Okay, so we have done with genetic algorithm and fuzzy logic. So now we'll be moving on to artificial neural networks. So probably you might be aware, or you might have heard about the artificial neural networks previously. Actually, artificial neural networks, it plays a major role, especially in the context of deep learning. So as of now, you know that deep learning is a buzzword where everybody wanted to learn the technology. So the actual concept behind deep learning is actually it is neural networks. It is, or you can call it as artificial neural networks. And these artificial neural networks concepts are actually inspired from biological neural network. It is inspired from biological neural network. It is the human neural system. The so if you consider the biological nervous system, the brain is the center part of the human nervous system. Brain is the center part of the human nervous system. That is, brain acts as the control center. It's not physically, it is not at the center. Of course, in the human body, it is at the top, but it is the control center. That is, every signal will reach brain, and the feeling, or the whatever the thoughts connected with any input that body receives, that is experienced through the by the brain through the nervous system. Okay, so a biological nervous system consists of a large number of interconnected processing units, and these processing units are called as neurons. Okay, so there are many interconnecting processing units in the human body, and these interconnecting processing units are called as neurons. Each neuron, if you take, it is approximately this is the size of a neuron. The size of a neuron is approximately 10 micrometer long, and these neurons can work in parallel. These neurons can work in parallel, so that as a human we can receive input from different sources, and we can process it simultaneously. Right? So it's not that the neurons are present only in the brain. No, throughout the body it is there. Okay, because the neural network, I mean the biological neural network, is there throughout the body, right? Okay, so at different places there will be some processing units. These processing units are called as neurons. And a human brain contains this many neurons, 10 to the power 11 neurons communicating with each other with the help of electrical impulses. So whatever the thing, the human nervous system that it receives from the environment, that will be converted to electrical signals, and this will be communicated from one neuron to another neuron depending on the strength of the signal. It is not that every information will be passed to every neuron. No. So depending on how intense the electrical impulse created, based on that, the number of how many adjacent neurons the signal will reach, that it will be decided by the strength of the signal. Okay. So this is the human brain with various parts. So this part is called as this gray matter is the brain. Okay. And this end of the brain is called the cerebellum, and this is the starting point of the spinal cord. So if you take any particular neuron, how it looks like. Okay. So if you take this is a neuron. So this neuron, this part or the actual neuron is called as soma. The actual neuron is called as soma, and there is a center. This is the center core part of the neuron, which is called as core. Okay, and whatever the branches that were thin branches that were going from the neuron, these branches are called as dendrites. These branches are called as dendrites, and some of these dendrites are called as synapses. Some of these dendrites are called as synapses. So which dendrite is called as a synapse? In the sense, the dendrite that connects with another neuron is called as a synapse. So this, if you call this as a synapse, then it means that it is going to connect with another neuron. Say for example, there is another neuron here, and this neuron also will have dendrites, right? So there is a suppose. Okay, so now this is a synapse because this synapse, this is called as this dendrite. We are calling it as synapse because this dendrite is used to get connected with the next neuron. Okay, so the dendrite that is connected with the another neuron is called as synapse, right? So here what happens in the sense, so these are the dendrites. So actually the inputs are received from the dendrite, from the external world. Say for example, a person is seeing something, or a person is experiencing some pain, or a person is feeling the wind, or whatever it may be, or feeling the heat. Everything, the signals are received through the dendrite. Okay, and depending on the degree of the input, it will be, so it's a biological input that will be converted to electrical pulse automatically by the nervous system, and it will send to the neuron, right? So like that, the neuron can receive input from several dendrites. So that depends. It is not that it should always receive only from one dendrite. It may parallelly receive input from several dendrites also. Okay, and depending on the strength of the signal, and all these signals will be reaching here to the soma or to the nucleus, and this nucleus then it will make some, what you call, it will make some collective decision. So whether all these things represents a same signal or they are different or not, that discrimination will be done by the soma, and finally it will come to a judgment, right? Okay, it is about heat, or it is about cold, or it is about wind, or it is mixed. It is a mixture of two things. Maybe this dendrite is sending information about heat, this is about something else. Then like that it will make the discrimination, right? And depending on the strength of this electrical signal, it may either go on to the next neuron or it may not go. So that depends on how much strong the signal is. So these are the things we have discussed. So dendrite is a bush of thin fiber which are emerging from the neuron, that is called as dendrite. Axon. Axon is the one which connects. This part is called as axon. So this lengthy part is called as axon. Okay. So these branches are called as dendrites. So axon is one which connects dendrites with the neuron, right? So that is called as axon. So axon is a long cylindrical fiber. So this is a long cylindrical fiber, whereas dendrite is a thin one, because dendrite is emerging from axon. So it will be comparatively smaller. Soma, it is also called as cell body, and it is something like a nucleus of the cell. It is something like how in every human cell there is a nucleus. So like that, the nucleus part of the neuron is called as soma. Okay, and again soma contains a core, right? So this is nucleus, that is called as soma. The nucleus of the neuron is called as soma, and this part is called as core. So core is different, this is different. Soma, or you can say that soma is otherwise called as the nucleus, right? Which is equivalent to the nucleus of the cell body. So the nucleus of the neuron is called as soma. To simply say, the nucleus of the neuron is called as the soma. Nucleus of a neuron is called as soma. Okay. Synapse, it is a junction where axon makes contact with the dendrites of neighboring dendrites. Okay. So it is a junction where the axon makes contact with the dendrites of neighboring dendrites. Okay. So where the dendrites of one axon connect with the dendrites of another axon. So that is called as synapse. And there is a chemical in each neuron. This chemical is called as neurotransmitter. It is because of this chemical only the signals are transmitted from one neuron to another neuron, provided if they exceed a certain threshold limit. Okay, but it is because of this chemical neurotransmitter only the signals are getting transmitted from one neuron to another neuron. So all inputs, so a signal is transmitted across neuron by this chemical. All inputs from other neuron arrive to a neuron through dendrites. Yes, these signals are accumulated at the synapse of the neuron and then serve as the output to be transmitted through the next neuron. Right. So the signal that is coming from one neuron, it will be accumulated in the synapse, and through the synapse it may travel to the next neuron provided the signal has sufficient strength. An action may produce an electrical impulse which usually lasts about a millisecond. Any action that we do, so that will create an electrical impulse which may last for about some milliseconds. So this pulse generated due to an incoming signal, and all signal may not produce pulses in axon unless it crosses a threshold value, right? So it is not that every signal will be processed by the neuron. So only if it exceeds a threshold limit it will be processed. Okay. So there may be some small things which is going on in the environment which we may not even sense because it means that it is not creating enough strength. So depending on the strength of the signal, it will be decided like whether a neuron can sense it or not. Okay, and also it is decided based on the strength of the signal whether the signal will be transmitted from one neuron to another neuron or not. Also note that an action signal in axon of a neuron is a commutative signal arrives at dendrites which summed up at soma. That is the action, what action to be taken, that will be decided by the sum of all the signals. It's a commutative signal. So for example, see this is a soma or a nucleus. Now this nucleus may receive signal from several dendrites. So finally they all will be a commutative signal will be generated here. Based on that the decision will be taken, like what to be done, how the human should react. Okay. So basically artificial neural networks are inspired from these biological neural networks. So in fact the human brain is a complex structure and it can be viewed as an interconnected network of processing units called neurons. So artificial neural networks, which is otherwise simply called as neural networks, these are the simplified models of biological nervous system. The artificial neural networks, it can also be called as just a neural network. These are nothing but the simplified model of the biological nervous system. So basically the concept of artificial neural network, it is something which is trying to model the human biological neural network. Okay, so we cannot model the human biological neural network as it is, because human biological neural network is very complex. Still, the scientist has not fully understood that how the human brain works, right? But still, at a top level, we can do some modeling, and by that we can solve some complex problems. So this is the basic unit of a biological neural network is neuron. The basic unit of a biological neural network is neuron, which is otherwise called as perceptron. The neuron is also called as perceptron. Okay, so this is the basic functional unit of a biological neuron. So if you consider the artificial neural network, in an artificial neural network also, the basic functional unit is perceptron. It's the same name. It is just inherited or derived from the biological neural network. So here also the basic functional unit is perceptron, right? So initially actually the computer scientists, they try to model the perceptron. So if you look at the what do you call, if you look at a normal neuron, how it works in the sense, it takes signal from several dendrites, okay, and finally it performs some what do you call it performs some commutative operation, okay. It adds up all these things, or it converts all this signal into one signal. Some commutative operation is going on here. Once that is done, it creates a single signal, and that single signal will be communicated through the axon, and depending on the strength of the signal, it may either reach the next neuron or it may not reach. So this is how normally the neuron behave. Now how can you model this? So mathematically this is modeled like this. So these are the various inputs, x1, x2, x3 up to xn. So these inputs are nothing but the inputs which are coming from the environment, and you can consider this as dendrites. So that is, every input corresponds to a dendrite, okay. And now these are the inputs, and for every input we will associate a weight. For the first input there will be a weight, for the second input there will be a weight, for the third input there will be a weight, and for the fourth input, like that, so on and so forth. For every input there will be a weight, and what we do is we perform weighted sum. So x1 will be multiplied with w1, x2 will be multiplied with w2, x3 will be multiplied with w3, so on and so forth. Xn will be multiplied with wn, and then we add everything. So that is what this summation says. So basically here, so this is the actual neuron. So in the neuron, what happens? In the biological neuron, it combines all the outputs by performing some commutative operation. Similarly here, what we do this x1 w1 plus x2 w2, so on and so forth, xn wn. That's what we do. So you can simply say that it is xi wi, right? So these inputs we know, but these weights we don't know. So the entire concept of neural network is identifying these weights. How will you identify the correct weight? So that is what the whole neural network is about. So initially we assume some random values for this weight, and then we keep on updating this weight until we get an ideal weight. Okay. So after deciding the weights, we perform this operation, and then we see what is the result. So depending on the result, if the result is more than a threshold value, then we say that the output is 1. If it is less than the threshold value, then we say that the output is 0. So if it is 1, it means that it is, you can say it is success, or the problem is solved successfully, or whatever you are searching, it is found, something like that. If it is 0, it means that it is unsuccessful, or the value that you are searching is not found, something like that. Okay. So this is how we model the neuron or perceptron. So in artificial neural networks also, this is called as perceptron. Okay. So this concept you should understand clearly. So here if you see the axon, this axon is, instead of axon, the axon is replaced here with this weighted sum part. Okay, sorry, not axon, the cell body. The cell body, or you can call it a soma or the nucleus. The nucleus is replaced with this weighted sum, and this signal will be traveling through the axon if it is beyond a certain threshold limit. So that is decided by this particular unit. So this unit, if you see here, this unit is called as threshold unit. This unit is called as threshold unit. So axon, cell body or nucleus is replaced by summation unit in the artificial neural network, and axon is replaced by threshold unit. Okay. So this is the brief introduction about artificial neural networks. So could someone summarize what we have discussed so far? Yes. Hmm. Yeah. Okay. What is a what is soma? What is meant by soma in biological neural systems? Yeah. So actually we don't use the term nucleus, but it is equivalent to a nucleus. In a normal cell, it is equivalent to the nucleus. What is dendrite? Yeah. And what is axon? Yeah. And what is synapse? Yeah, that is synapse. So what's the difference between synapse and dendrites? What's the difference between synapse and dendrites? All dendrites may not be synapse, right? So it is not that every dendrite should be connected with some other neuron. So whichever the dendrite which is connected with some other neuron, that is called as synapse. And what actually the cell body does in the biological nervous system? It receives input from all the dendrites, and it performs some, and it combines all the inputs by performing some commutative operation. Okay. So what is here? Yeah. So depending on the strength, the signal will be either transmitted to the next neuron, or it may not transmitted. Okay. So what is the equivalent of this nucleus in the artificial neural network? Weight, not weight, not weight. What is equivalent to this part? This combines every inputs. So the equivalent of this is summation. This is the equivalent of this, and the equivalent of axon is threshold. Yeah, because only if the strength is good, it will be transmitted through the axon, and it will reach the next nucleus, next neuron, right? But our whole purpose here is to identify the weights, right? It is identifying the correct weight, so that because input is coming from the environment, but what we don't know the weight. Yeah. So how are we going to identify the weight? So when you adjust the weight appropriately, the neural network will behave properly, right? So these are the inputs. This is the weight, this is the summation unit, this is the threshold unit, and this is the output. Okay. So whatever we have discussed there, that is explained here. Right. it can be further, it can be represented like this. Say for example, these are the inputs x1, x2 up to xn, and these are the weights. Initially we don't know the weights, but let us assume that weight is known. So w1, w2 up to wn, and this is the summation unit. What it actually performs, in the sense it performs this w1 x1 plus w2 x2, so on and so forth up to wn xn. That is summation I is equal to 1 to n wi xi. So let us assume this entire term is called as I. This sigma I equal to 1 to n wi xi, say that it is called as I. So the output of this is I. And for on I we operate on one function, that is we call it as phi of I. So if phi of I, so that is whatever the output coming from the summation unit, on that you are applying some function. If the output of that function is greater than a threshold unit, then we say that the output is 1, otherwise we say that the output is 0. That is called as y. So you can say that y is equal to phi of I. And what is I? Y is the output. Yeah, yeah, yeah. I is nothing but sigma I equal to 1 to n wi xi. Fine. So basically there will be a parameter called theta. So this theta is nothing but the threshold. This theta is nothing but the threshold. So if, for example, if wi xi is, I mean if the summation of wi xi is greater than theta, then I, that is I is greater than theta. I is nothing but what? Summation of wi xi. If I is greater than theta, then the output will be 1. If I is less than or equal to theta, then the output will be 0. So this is in case of binary classifier. This is a simple case we are discussing. The simple case where a neural network can be used is, it is a binary classifier. Binary classifier means whether yes or no. So if it is 1, we say it is yes. If it is 0, we say it is no. Right? Say for example, what kind of example you can consider in the sense, for example, assume a neural network takes a particular photo as an input, and it says whether this photo is a photo of a human or not. An image it takes as an input. So it has to just say whether it is an image of a human being or not. So if it is an image of a human being, it should say, yeah, it should output as 1, otherwise it should output as 0. So this is an example of a binary classifier. Or you can say it will take an image and it will say whether it is a cat or not. So if it is a cat, then it should say 1. Suppose if the image is not of a cat, if it is of a dog, then it should say 0. Okay. So such classifiers are called as binary classifier. So using a single perceptron, what you can do is you can only use it for a binary classifier. Okay. That too for a small problem. You cannot use it for a complex problem. But whatever the output it gives, the actual output is I. But I, again we compare it with theta, some threshold limit. If it exceeds the threshold limit, then we output as 1, which means it is true. Yes, what you are looking for is available in this input. If it is 0, which means it is false. No, this is not the input that you are looking for. Okay. So that theta we are subtracting here. So whatever the threshold, we are subtracting it here. Why we are subtracting like this? Because first we take the summation. After summation we are subtracting. Suppose if this value is greater than theta, okay, then what will be the result of this subtraction? This is nothing but I. Okay. So if I is greater than theta, then the result of this subtraction will be what? Not 1. It will be greater than what? You cannot say 1. It will be only, that is reserved by here separately. This is only I am asking this I minus theta. If I is greater than theta, then what will be I minus theta? It will be greater than what? Greater than theta, that is fine. But something else, it is greater than, what else you can say? Say wi xi is 10. Say theta is 8. What is 10 minus 8? 2. So it is greater than what? I will give another example. Say WIXI is 10. Say theta is 12. Now what is 10 minus 12? So how this input and this how this two differs? This is greater than. Now this is greater than what and this is greater. This is greater than 0. This is less than 0, right? So this is, you can say this is greater than 0 and you can say this is less than or equal to, or you can say this is greater than or equal to 0 and this is less than 0. Okay. So whenever you can say, so what you can identify in the sense, after doing this, if the output is greater than or equal to 0, okay, after performing this operation, if the output is greater than or equal to 0, then what does it mean? Then WIXI is greater than theta, right? So then it will be 1. Okay, are you getting? If it is, yeah, if it is greater than 0, if it is greater than 0, then it is greater than theta, then it will be 1. Okay, otherwise it will be 0, right? So that is what here we are doing. So 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 either you can check whether directly I greater than theta or not, or you can subtract like this and you can see whether the output is greater than 0 or not. If it is greater than 0, then whatever the output, it will be converted to 1. If it is less than or equal to 0, the output will be converted to 0, right? Okay. So this function, so whatever here, this operation we are doing, no, checking whether I is greater than theta or less than or equal to theta, this function is called as Heaviside function. Okay, it's a step function which is called as Heaviside function. Okay, so this is also called as transfer limit. So whatever this operation we are performing, this is otherwise called as transfer limit. Transfer limit, that is, this only decides like what is the output, whether the output is 1 or 0. So this is otherwise called as transfer limit. I think the diagram, it might be mentioned. Okay, no. So you can also call it as transfer limit. So there are two types of transfer function we have. Okay, or you can simply call it as transfer function. So you can also call this phi as a transfer function. This can be called as a transfer function. So we have generally two types of transfer function. One is called as hard limit transfer function. The other one is called as signum transfer function. So what's the difference in the sense? Actually, this is an example for a hard limit transfer function. So the hard limit transfer function, what it does in the sense, if the output is greater than theta, if it will make it as 1. If the output is less than or equal to theta, it will make it as 0. That is called as hard limit transfer function. Okay. The second is called as signum transfer function. Signum transfer function, what it does in the sense, if the output is greater than theta, then the final output will be converted to 1, which is same. But if the output is less than or equal to theta, then the final output will be converted to minus 1. So that is called as signum transfer function. Okay. So that is what this diagram says. So this diagram, what it says in the sense, so this left side one, it is hard limit transfer function. That is, if the output is, so say this point is theta, say in x-axis, say this point is theta. If the output is less than or equal to theta, then the final output will be 0. If the output is greater than theta, then the final output will be 1. That is what it says. Okay. So this is hard limit transfer function. Whereas in a signum transfer function, again now this point is the theta. If the output is less than or equal to theta, then the final output will be minus 1. Okay. If the output is less than or equal to theta, this point is theta. So if the actual output is less than or equal to theta, then the final output will be minus 1. If the output is greater than theta, then the final output will be 1. Okay. So what's the difference between hard limit transfer function and signum transfer function? Yes. How hard limit transfer function differs from signum transfer function? Okay, fine. So that's the difference. So I think you are understanding this graph. So this is the same thing. So this is nothing but whichever we have discussed previously, that is nothing but a hard limit transfer function, and this is the mathematical representation of the signum transfer function. When I is greater than theta, it is plus 1, otherwise it is minus 1. So there are also other transfer function. So this is a very famous transfer function in deep learning. So this transfer function is called a sigmoid transfer function. This transfer function is called a sigmoid transfer function. There are two types of sigmoid transfer function. One is called as log sigmoid transfer function. This first function, so the function is only this much. This is just the name. Okay, don't get confused. This is not part of the function. So this first function is called as log sigmoid transfer function, and the second function is called as tan sigmoid transfer function. So what this sigmoid function does in the sense, see the previous transfer function, whatever we have discussed, the odd limit transfer function and linear transfer function. The signum transfer function is otherwise called as linear transfer function. Okay, so those transfer functions, what they does in the sense, their final input will be either 0 or 1 or minus 1 or 1. Okay, that is, it cannot give any input between this. But say that I want an input between this. So that is, it is going to give a concrete input either 0 or 1. And this is also the linear function is also going to give either minus 1 or 1. It won't give anything in between that. Right? But say that we want the in between values also as the output. So I want to know whether something is, what's the actual output, that is 0.6 or 0.7 or it's 0.3 or what. Okay, right? So for example, if you want to find whether something is a cat or not, then if the output is 0.6, it means it is somewhat resembling to cat. That is what you can say, right? Or so maybe there may be some threshold again. If it is 0.9, if it is more than 0.9, we will confirm as cat. But if it is 0.8, then you can say that it is very much close to a cat. So it may be belonging to some other cat family. Okay. So like that, I want to find the in between values also. If you want to know the in between values also, then in that case you have to use the sigmoid function. So sigmoid function. So basically, the sigmoid function is in a simple form. The log sigmoid function is just represented like this. It is 1 by 1 plus e to the power minus x. The x is the input, or you can say x is the actual final output. In our case, we are calling it as I. In our case, we are calling it as I. I is nothing but sigma I equal to 1 to n wixi. Okay. So, or I will call it as I only. So whatever this output you are getting, you just plug in here. 1 by 1 plus e to the power minus I. So now if you do it for different values, what you will get in the sense, you will not get a rigid one. The previous function, whatever we have discussed, they are rigid. These two are rigid function. Rigid in the sense they give fixed values. Either their output will be 0 or 1. In this case, it is minus 1 or 1. They don't give any input, any in between values. So we say this is rigid. So they are very specific about the output. It's not smooth. Whereas if you see the sigmoid, if you apply different values of I, you will get a smooth function. Okay. So anyway, but sigmoid, log sigmoid will be between, the output will be always between 0 and 1. 0 and 1. And this tan sigmoid, if you see, the output will be between minus 1 and plus 1. So that is the difference. Okay. So if you see log sigmoid, the output will be something like this. It will be between 0 and 1, whereas tan sigmoid will be between minus 1 and plus 1, right? So the actual formula is this, whatever I have written here, it is the actual formula is it is this e to the power minus I. Okay, but here if you see in our formula, it is written as 1 by 1 plus e to the power minus alpha I. So this alpha is another parameter which we are including to control this curve, to control this curve. So how much this, how this curve shape should be, whether whether it should be what you call biased in one end or biased in another end. If you can adjust this curve by adjusting this alpha value. Okay, for example, if alpha is 0.5, if alpha is 0.5, then this curve will be something like this. Okay, it will be more or less a straight one. It will be something like this. Okay, right. Good. So by changing the different value of alpha, so alpha should take value between only 0 and 1. Okay. So by different values of, by applying different values of alpha, this shape of the curve can be changed. So basically that is the idea. So here also you have this alpha. So the actual formula, if you refer other materials for neural networks, they won't include this alpha, right? But here in our textbook or in whatever the material we are referring, alpha is included. But just you try to, just you understand that alpha is used to control the shape of the sigmoid curve. So the, here also if you see the actual formula is only e to the power I minus e to the power minus I divided by e to the power I plus e to the power minus I. That's it. So this is what is called as tan sigmoid. Tan sigmoid is given like this. Okay, e to the power I minus e to the power minus I divided by e to the power I plus e to the power minus I. But we are including one more parameter alpha. Again, this alpha is used to control the shape of the curve. So you can see here. So this is correspond to the rigid function. That is whatever the original function which we have discussed. That is hard limit transfer function or linear transfer function. So this is for the hard limit transfer function. This is for the linear transfer function. So this is the case for sigmoid transfer function. So when you use sigmoid transfer function, and if alpha is 0.5, then this is the curve. This dotted line represents alpha 0.5. You can see it is going from 0 to 1. Okay, right. So it is, but it is taking different values, right? So what you have to consider is the point in x. Okay, and if alpha is this is for 0.5. If alpha is 1, not 10, this is 1.0. If alpha is 1, then this is the curve. The curve shape is different. If alpha is 0.3, then this is the curve. Okay. So different value for alpha, you are getting different curve. So this curve can be controlled by changing the value of alpha. Similarly, for tan sigmoid function, it takes value between 0 and 1. So it's a smooth function. So it is taking values between 0 and 1, minus 1 and 0. This log sigmoid, it takes between 0 and 1. This takes between minus 1 and 0. Okay. So you can see here it is going from, so again this is 0.5, it is going from here to here. If that is when alpha is 0.5, when alpha is 1, it is going from here to here. When alpha is 0.3, it goes from here to here. Okay. So what's the difference between a normal transfer function and sigmoid transfer function? Yeah, if you get in between 0 and 1, that is called as, yes, if you get between minus 1 and plus 1, that is called as, yes, okay. So these formulas and all you should remember, this will go a long way. Okay, so throughout machine learning, deep learning, this will be used, especially this sigmoid function, you will be using it heavily because of late the output should be converted to, we want an output between 0 and 1. So mostly we take this log sigmoid function. So the idea is whatever the output that is coming out of the neural network, that will be given to a transfer function. So there are many such transfer function is available. So one of the commonly used transfer function is this sigmoid function. And so let us see what are the advantages of artificial neural networks. So the basically artificial neural networks are used to map the input with the output, and these artificial neural networks, it can learn by examples. So mainly in deep learning we are using artificial neural networks because they can learn by example, like uh, so learn by example in the sense, normally we give some input, and whatever the output comes, if the output is not according to your expectation, then the based on the output we can update the weight. Based on the output we can update the weight. So that is called as feedback. That is called as feedback. So based on that, the weight will be automatically updated, and hence it learns, and finally it will identify the correct weight for which the algorithm works in a optimal way. So that is how the entire deep learning works, right? There are different types of neural networks available, like single layer neural network, multi-layer neural network, feed-forward neural network, feedback neural network. Okay, so this deep learning actually it is a part of feedback neural network. It will give feedback. It is once you given an input and some random weight, you will calculate something called as error. So the error will tell you like how much we are away from the actual output, right? And based on that, the weights will be updated. So that is how it learns. So we'll be probably will be discussing that in later part. Okay. So the ANNs are robust and fault tolerant, and they can therefore recall full patterns from incomplete, partial, or noisy patterns. So that is, even if the input is incomplete or partial or noisy, the system can learn, because you are not going to give only one input, you are going to give plenty of inputs, and then you are going to make it learn. Okay. See, one of the main drawback with deep learning or artificial neural network is it produces the advantage is it produces good result. That is, you can say it has a very high accuracy. That is its advantage. But its disadvantage is they are not, what do you call, you cannot verify the output. I mean, their interpretability is very less. You cannot interpret the neural network, and you cannot try to understand like why it is giving this output. This interpreting is very difficult, or this interpreting is a very costly operation. If you want to interpret, then you need a huge computational resource, which is actually very difficult at this point of time. So with neural network we are able to produce great results, like if you see image classification. Actually, neural networks or deep learning has surpassed the human efficiency. Humans are not now best in image classification. Actually, neural networks are best. For example, so classification in the sense not broad classification. Say for example, if you take cat, there may be different types of cat. Like there may be multiple categories, right? So even if a person who is a very expert in a cat, he may find difficult to differentiate one category of cat from another category, but neural networks can do. So its error rate is now less than 2%, which is better than a human error rate. The human expert's error rate is around 6 or 7%. Okay. So neural networks has surpassed in this area, especially in image classification, it has surpassed human efficiency. But still, one of the what you call comment from scientific community is about deep learning is its interpretability. There is a question on its interpretability. The system is not interpretable. Somehow it gives the output, but does it giving the output for the right reason? That we don't know. Are you getting? But actually, this question is crucial. This question is crucial because it is not only giving the answer, whether you have the right understanding to give that answer or not. Okay, so that is what it says about, right? So it is something like this. Say for example, somebody is asking you like how to go to so and so place. Okay, from somebody is asking, right? Say you know, assume that you don't know exactly how to go there, but simply you say that you go left, you will reach there. That person going in the left and he actually reached there. So, so now you are accurate according to this person, but that doesn't mean that you gave this information with the right knowledge. No, simply you gave, but that becomes right. So, is that is happening with neural network? That is a question. Okay. So, so is it understanding it in a proper way, like how a human understand, or how it interprets? That still we don't know. So this is the introduction to neural networks. Okay, now we will continue with the with this. So there are different types of neural network architectures we have. Say for example, these are the commonly used three important architectures. The first one is called as single layer feed forward architecture. The second one is multi-layer feed forward architecture, and the third one is recurrent network architecture. Okay. See, let us take a 5 minute break. My battery is going down. It is somewhere else. I'll just join, right? You can have a 5 minute break meanwhile. Okay, sorry. So let us continue. Yeah, yeah. Thanks for waiting. So basically, we have different style of neural networks, or you can call it as architecture. So basically, these are the three neural network architectures which are available in general. So these are called as single layer feed forward architecture, multi-layer feed forward architecture, and recurrent network architecture.
Sir, your voice is not audible.
Okay, 1 minute. Am I audible now? Am I audible? Am I audible? No. Am I audible now? Okay, fine. So it went on to mute. So let us continue. So there are three types of neural network architectures. These are single layer feed forward architecture, multi-layer feed forward architecture, and recurrent network architecture. Out of all these three, only this recurrent architecture talks about feedback. So in this two architecture, there is nothing like feedback. Feedback in the sense the output will be again fed as the input to the neural network, and based on that, the weights will be updated. So in these two cases, there is nothing like feedback. So they are called as feed forward architectures. Whereas this is a feedback network. There are different types of feedback networks available, but all the neural networks with feedback are grouped together in one particular category, and that category is called as recurrent network architecture, right? So recurrent architecture means basically you can understand that it is a feedback based architecture, whereas the other things are without feedback, so they are called as feed forward architectures. So we'll understand the working of neural network with the uh, based on the logic and. So now the logic gates and how and works. So with that input, with the and logic, we'll try to understand the working of a neural network in a simple case. So you know that this is how the Boolean operation and works. It has two inputs and one output. So if the input is 0 0, the output is 0, 0 1, again the output is 0, 1 0, the output is 0. When the input is 1 1, the output will be 1. Okay. Now this can be represented as a neural network, something like this. So in this case, the number of inputs is only 2. So you can say there are two inputs, x1 and x2, and and this x1 should be connected with some weight w1, and x2 should be connected with some weight w2. And then what we do is we perform x1 w1 and x2 w2. So that result will be generated, and then we have to identify some threshold value, which is uh, some threshold value, say theta. So if the output is greater than theta, this is I, right? So if the output is greater than theta, then we should say that final output as 1. Otherwise we'll say the final output as 0, because here in the AND gate you can see the output is either 0 or 1. So now the question is here, what are the things we have to identify? We have to identify what is W1, what is W2, we should identify. X1, X2 is known. So these are the different combinations of x1, x2. One combination is 0, 0, another combination is 0, 1, another combination is 1, 0, another combination is 1, 1. But we should identify a common W1 and W2 which is applicable for all values, for any value of x1 and x2, such a way that the output I, if it is greater than theta, this theta also we should figure out what this theta also we should identify what should be the threshold limit. So if I is greater than theta, then we will give the output as 1. If I is less than theta, then we will say the output as 0. Okay. So could you make some random guess for the value of theta, for the value of W1 and W2 in this problem? Is the question is clear? Here, what are the things we should identify to solve this problem using neural network? Yeah, weight. What are the weights? Yeah, and yeah, theta, what threshold limit. These three things, yeah, we have to identify. So, could you guess anything for W1 and W2? Any idea? Yes. Let us say I will say the value for theta. Let us assume theta is 0.9. Okay, that is only if theta is greater, only if I is greater than 0.9, then only it should output 1, otherwise it should output 0. In that case, what value will you give for W1 and W2? This will be, you know, right, this x1 can be either 0 or 1, x2 can be also either 0 or 1. So this is either 0 or 1. So these are the different combinations, 0, 0, 0, 1, 1, 0, 1, 1. So for what value of W1 and W2, I will be greater than, I should be greater than 0.9 only for which case? Only for this 1, 1 case. In all other case, it should be less than 0.9. So what value you can think for W1 and W2? Yes. Okay, so here is an solution is given. This is one solution. Okay, there can be different way of solving this. Let us assume W1 as 0.5 and W2 as 0.5 and theta as 0.9. Theta is 0.9. Okay, so this is one solution for this problem. So now if you say, if assume x1 as 0 and x2 is 0, then what is x1 W1 plus x2 W2? Take the, no, 0, x1 is 0, x2 is also 0. So what sigma output is what? 0, right? So 0, so then, so is 0 is greater than 0.9 or less than or equal to 0.9? Yeah, it is less than 0.9. Okay, so what happens? So the output will be 0. Okay, in this case. Second case, assume the output input is 0, 1. If it is 0, 1, what will be the output? The first level output? Then I mean I will be 0.5. That is 0 into 0.5 plus 1 into 0.5, which is 0.5. Is 0.5 greater than 0.9? So what should be the final output? 0. Third case, assume 1, 0. If it is 1, 0, what will be I? Again, same. So what will be the final output? 0. And the last case is 1, 1. So if it is 1, 1, what will be I? 1. Yeah, because x1 is 1, 1 into 0.5 plus 1 into 0.5, which is 1. 0.5 plus 0.5 is 1. So if 1 is greater than 0.9, so what will be the final output? 1. Okay. So this is one way of solving this. So actually you need not keep this 0.9, even you can keep it 0.7 or 0.6 also will work, right? Because here all these outputs are always less than 0.7 or 0.6. Okay. So But anyway, you have to identify what these are the things we have to identify. Point this W1, W2, and this theta. Okay, the threshold limit. So these are the parameters which you have to identify. W1 you have to identify, W2 you have to identify, and this theta thing you have to identify. Okay. So the point is, this is a simple case. So here we can manually, with how we identified this is 0.5, this is 0.5, this is 0.9 or 0.7, by some error and trial, right? We can identify it easily. But not for all the problems you cannot identify that easily, because you may have many inputs. Here you have only 2 inputs. If you have 10 inputs, if x1, x2 up to x10 is there or x20 is there, then so many weights you have to identify, and you have to identify this threshold limit. So all these things you cannot do manually. So this process should be automated. Okay, so that is what is happening in the neural network, right? But this is the way. This is just for your understanding how it exactly is working. So our final objective is to identify these weights, right? So now with this understanding, let us see how a single layer neural network works. Single layer feed forward neural network. Single layer means there is only one layer. So that is the input layer and that is the output layer. So in this diagram you can see there is only one layer. So this is called as layer. This is called as layer. This layer can have any number of neuron. So this is a single neuron. In this case, this is a single neuron. But this is a single layer. This is one layer. This is the layer, and this layer contains n number of neurons. I1, I2 up to In. There are n neurons are there. Okay, and these are the different inputs. How many inputs? We have m inputs are there. X1, X2, X3 up to xm inputs are there, right? And every input, if you see, it is connected with every other neuron. So that such a network is called as a fully connected network. If every input is connected with every neuron, then that is called as a fully connected neural network. So it is not required that all neural networks should be fully connected. It may not be fully connected also. So fully connected means then you are looking for all possible combination. Here if you take this input x1, it is connected with all these neurons. It is connected with the first neuron through the weight W11. It is connected with the second neuron through the weight W12. It is connected with the third neuron through the weight W13. So on and so forth. It is connected with the nth neuron through the weight W1n. Similarly, if you take x2, it is connected with the first neuron. So this will be the weight W21, and it is connected with the second neuron through the weight W22, and with the third neuron through the weight W23, and through the nth neuron through the weight W2n. Like that, all neurons are connected with, all inputs are connected with every other neuron, right? And all these neuron will perform sum, and all these neuron will perform the what you call weighted sum, and they will produce some output based on the threshold. So this threshold limit now may vary for different neuron, okay, and this weight also may vary, right? So for example, the threshold limit for the first neuron may be 0.9, for second neuron may be 0.7, for this may be 0.4. So accordingly it will produce the output. And now you are getting multiple outputs, not one output. So based on this output, we will decide something. Maybe this output may be 1, this may be 0, this may be 1, so on and so forth. Some values you will get. So based on this value, we'll be finally deciding what is that, right? Or in some cases this is used for multi-class classification. Multi-class classification means, say for example, you give an image and you want to identify what are the objects present in this image. Say for example, let us consider only here there are m inputs, so there are, and also it shows there are n outputs are there. Let us assume there are only 3 outputs. Say the first output says whether this image contains a cat or not. So the second output says whether the image contains a dog or not. So the third output says whether the image contains a human or not. Okay. So if there is a cat in this image and if there is a human in this image, but there is no dog in this image, something else is there, a tree is there, some other ball is there. Okay, in that case it will give one for cat and one for human, but the dog part will be 0, right? If there is a dog alone is there in the image, there is no cat or a human, then this alone will be 1 and this will be 0, right? So like that, how you are going to use this, that depends on the type of the problem, right? The point here what we are discussing is, this is an example for a single layer feed forward neural network. Why we are calling as feed forward? Because there is no feedback here, the output is not fed back to the input, so it is called as feed forward neural network, and here there is only one layer, right? Okay, so could someone summarize what are the different neural networks architectures we have? Hmm. Hmm. Yeah, what is recurrent network? Yeah, the other two are not feedback. Okay, again in recurrent network, we have different types of recurrent networks. So based on how the feedback is given, they are further categorized. And what is meant by, what do you understand from single layer neural network? Single layer feed forward neural network? What are the components are there? Yes. No, no, that is single neural network. That is single neuron. Here I'm talking about single layer neural, single layer feed forward neural network. This one. Here, do we have only one neuron? Yeah, we have only one layer. We have only one layer. One. This is called as layer one. Okay. If you have multiple layers like this, then that is called as multi-layer. This is only one layer, but we have more. How many neurons here we have in this network? N neurons are there, and how many inputs are there? M inputs, and each input is connected with, not respective neuron. Each input is connected with every other neuron, right? Every neuron is every input is connected with other all neurons, right? If you take this input, it is connected with every neuron. So if you take this input, it is also connected with every neuron, and the neurons are connected with the and the input is connected with the neurons through weights. So so if you take the neuron, say xk, okay, it will have, if you have the input, if you take the input xk, it will have how many weights? Wk weights. Okay, what are the weights? What will be the first weight? Wk1, w, and then wk2 up to kn. Why n? Because how many neuron we have? N neurons. So we have, so you have wkn neurons. So totally how many weights you have? Only n weights. This k is constant, right? K is not, no, with respect to k we have only n weights. Repeating. With respect to input k we have only n weights. Of course, like that you have for x1 you have n weights, x2 you have n weights, xk you have n weights, xm also you have how many weights? N weights. That is wm1, wm2 up to wmn. So totally then how many weights will be there? Each x contains n weights. How many x we have? How many such x we have? M. So totally, how many weights will be there? Total number of weights will be, pardon? Not m power n. M into n, right? M cross n, right? There will be m cross n weight, right? So in case of a fully connected neural network, right? And each neuron will have its own threshold limit. Threshold limit need not be same for all neurons. Every neuron will have its own threshold limit, and whatever the output comes, that is the based on the threshold, the output will be decided. So this is the structure of a single layer feed forward neural network. Okay. So this is same thing whatever we have discussed. And so in a single layer feed forward neural network, the entire weights that is available in a single layer feed forward neural network can be represented through a weight matrix. Because our whole logic is what? Our whole logic is to find the weight. Find the weight and find the theta. What is the weight, correct weight we have to find, and what is the correct theta we have to find. Right? So this is the whole problem is. So whatever the weights, as we have already understood, there will be, in this case there will be m into n weights. So this m into n weights can be represented through a weight matrix. So this is called as a weight matrix W, capital W, which is nothing but W11. So in this first row, what it represents? First row, what it represents? First row is W11, W12, W13, so on and so forth, W1n. So what is that? So these are the weights corresponding to whom? Not weight 1. Which input? These first, pardon? M. No. See, what are the inputs? X1 to XM. These are the inputs. So these weights corresponds to which input? These are the weights, and these are the neurons. So we have n neurons. Neuron 1, 2 up to neuron n. So this is neuron 1 and this is neuron n. First input will be connected to first neuron, second neuron, third neuron up to nth neuron. Okay. This weight is what? This is 1 1, right? This is second weight is 1 2. This is so on and so forth. The last weight is weight 1n. Okay. So all these weights corresponds to which input? X1, first input. Okay. So that's what I am asking. This first row corresponds to what? Which input? First input. Second row corresponds to, the first row corresponds to the weight of the first input. The second row corresponds to the weight of the second input. So on and so forth. The kth row corresponds to the weight of the, and the last row, mth row, corresponds to the weight of the mth input, right? So for each input, what is the weight we have to identify? So that is the whole task is. So totally we have to identify this many weights, m into n weights, right? Okay. And what is the output? What is the output of this? What is the output of this neuron? Pardon? W? W? Come again? No. Why are you saying x1? Say in terms of x1 into x1. Yeah, fine, right? X1 into W. W11, right? Only that. But this is what? This is a neuron. This neuron, will it take only input from x1? It will take from x2 also, right? So x2's what will come? W21. Okay, and x2's this one here also it will go W22. Now, but I'm only talking about the first neuron. So it will be x1 W1 plus 21 plus so on and so forth. WM1, right? M1. So this is what this is nothing but the output of the first neuron, right? Okay. What will be the output of the second neuron? From x1 it is taking which input? W12, x2 W22, x3 W32, so on and so forth up to xm WM2. 2 is constant. Okay, the first one is constant. This one is constant. This will change. Okay, here 2 is constant, right? So this is what, this is the output of the second what do you call second neuron. What will be the output of the third neuron? uh, 1 3 or 3 1? Yeah, 1 3. Fine. Yeah, x1 into w13 plus, yeah, x1 w13 plus x3, yeah, x4 w43, so on and so forth, xm wm3, right? Hmm. So like that we have to identify the output of each neuron, right? So how can we make it generalized this? So like that for every neuron the output will be, you have to identify the output. So this can be generalized something like this, theta k. So theta, I mean, yeah, this is theta k or OK, whatever it may be. So O is nothing but the neuron. So the output of the, so O1 means the output of the first neuron. O1 is nothing but F1 of sigma I equal to 1 to M. Are you getting why we are going from 1 to M? Because for every neuron you have to go from 1 to M. 1 to M Wik xi plus theta k. This you can ignore. This is just to check whether it crosses the threshold limit or not. If when k is 1, when k is 1, what will be this function will give? W W11 x1 plus W11 x1 plus 12 x2 W, so on and so forth, right? Okay. So basically this formula shows like how for the uh, what will be the output of the kth neuron. Okay, I think this should be k. Yeah, k should be constant, right? Yeah, that's correct. Yes. Okay, fine. So that's what it works. Okay. Now let us discuss about So this is about single layer feed forward neural network. Now let us discuss about multi-layer feed forward neural network. Okay. So in case of multi-layer feed forward neural network, what we have is we have more than one layers. It's not just one layer, we have more than one layer. So there will be an input layer and there will be an output layer, and in between you can have any number of hidden layer. This is the simplest form. In a simple form of multi-layer feed-forward neural network, there is one input layer, one output layer, and one hidden layer. But actually, in reality, you can have any number of hidden layers. So if you look if you look into a deep neural networks, a deep neural network will have so many hidden layers. It will have so many hidden layers, and lot of processing will be happening, right? Okay, so the first layer is called as input layer, so this is called as I. So here in the first layer, let us assume there are I number of neurons are there, and and it is not that all the layers should have equal number of neurons. No, it depends. So the number of neurons in each layer may vary. For example, in the first layer you may have 10 neurons. Okay, in the hidden layer you may have only 4 neurons, and again in the last layer you may have 8 neurons, right? So there is no what you call, there's nothing like mandatory that the number of neurons should be same in all the layers. No, it's not like that. The number of neurons may vary, right? Okay. So the concept of multi-layer is just this is how we can define. There will be surely one input layer and one output layer. Apart from that, there can be any number of hidden layers. So, so the simplest form of multi-layer feed-forward neural network is to have one input layer, one output layer, and one hidden layer. And here we are assuming that the input layer contains I neurons and the hidden layer contains M neurons. Okay, and the output layer contains N neurons, right? So the hidden layer, the input layer contains I neurons, the uh, hidden layer contains M neurons, and the output layer contains N neurons. So this is an example. So if you want to generalize this, if you want to generalize a multi-layer feed-forward neural network, then a generalized multi-layer feed-forward neural network can have any number of intermediate layers. These intermediate layers are otherwise called as hidden layers, right? So a multi-layer feed-forward neural network will have I input neurons. That is, the input layer will have I neurons. Okay, and there can be any number of hidden layers. So let us assume there are p hidden layers. So if there are p hidden layers, then you can name each of the hidden layers as m1, m2, so on and so forth up to mp. So these are the different hidden layers, right? And each of these p hidden layers can contain different number of neurons, right? So it is not that each hidden layer should have same number of neurons. It can have the number of neurons may vary from one hidden layer to another hidden layer. Okay, and the last layer, the output layer, may have n neurons. So such a network can be called as I m1 m2 mp n network. Okay, such a network can be called as I m1 m2 so on and so forth mp n networks. Okay, so if you have only 3 layers, then you can call it as I m n network. So this is a simplest case of an multi-layer feed-forward neural network with three input, with one input layer, one hidden layer or middle layer or intermediate layer, and one output layer. So here you can see how many weights you have to calculate. Not only weights, apart from that we have to also calculate the threshold. So for each of these function, say for each of the number of neurons in the input layer. In the input layer we have I neurons. For each of these I neurons we have to identify the theta, that is the threshold. And for all these hidden layers, there are m neurons in the hidden layer. So this m threshold also you have to identify. And in the output layer there are n threshold you have to identify. So threshold itself you have to identify this many. I plus m plus n threshold you have to identify. All these are different threshold values. Okay, and if you take the input, so x1 weights, so with respect to x1, w11, w12, W13, so on and so forth, W1I, okay, because there are I neurons, right? W1I. With respect to X2, there will be W21, W22, W2I, so on and so forth with respect to XP. So let us assume there are P inputs are there. The number of inputs are P. So this will be XP1, XP2 up to XPI. So between the input and the first layer itself, if you see the weight matrix, what will be the size of this weight matrix? Between between input layer, between this input and the first layer, the input layer, what will be the size of the weight matrix? How many inputs are there? How many inputs are here? Yes. How many inputs are here? X1, X2, like that. How many we have? No, this is P inputs. Okay, XP. How many neurons are there in the first layer, the input layer? How many neurons are there in the first layer? I neurons are here in the first layer. Second layer, there are M neurons. In the last layer, I mean the hidden layer, M neurons are there. In the output layer, N neurons are there. So how many layers are in the first neuron? In the first layer, I neurons. Okay. So what will be the size of this weight matrix? P cross I. Yes. So this alone, I mean this weights alone, this set of weights alone, how many weights? P cross I weights. Is that is clear? So what will be the weight of this two? In between these two, there will be a, if you create a weight matrix for this, what will be the size of this weight matrix? Pardon? Why P? Here how many neurons you have? In the first, I. In here M. So how many? I cross M. So this weight will be what? This is the output from the first one. I mean first neuron. So this will be W11, W12, so on and so forth up to W1M. This will be W21, 22, W2M. Like that, this is WI1, I2, WIM. So it is I into M. The size of the weight matrix here. What will be the size of the weight matrix in between these two? M cross M. So these many parameters you have to identify. Okay. So this is the, actually this is a simple case. This is a simple case for understanding we are discussing with only one input layer, one middle layer and one output layer. But in reality, you may have 10 hidden layers or 20 hidden layers like that. Then you can see the degree of complexity which will be involved, right? And if you see a normal image classification, normally we image is represented as pixels, right? Even if you take a small image of what you call 650 by 650 pixels, if you stretch it out, it will have this many pixels, 650 into 650. Then that many inputs will be there, right? Then you can think of how many calculations will be happening. Okay, so we are not discussing all those things in detail, but this is at the top level we are understanding like how these neural networks were working. So this is about what you call, this is about multi-layer feed-forward neural network. And again here also you will have threshold. Okay, every layer there will be threshold, and this threshold also you should find out. Okay, so whatever we have discussed so far, that's what explained here. And coming to recurrent neural network, in recurrent neural network there will be feedback. So if there is a feedback is available, then such networks are called as recurrent neural network. So this feedback, the style of the feedback can vary. For example, see this, the output is directly fed to the input layer. The output of the final layer, output layer is given to the input layer. Whereas in this case, the output of this layer itself is given as an input for the same layer. So this is a neuron. Its own output is given as the input again. Okay. Whereas in this case, the output layer the output of the final layer is given as an input to the previous layer. So like that, there are different ways in which the feedback can be done. So based on that, they can be called as either Hopfield network, Boltzmann network, so on and so forth. So we are not going into the detail, but at the top level you understand that there are different styles in which the feedback can be given, and depending on the type of the feedback, this recurrent neural network can take different names like Hopfield network or Boltzmann machine, so on and so forth. Fine. Let us stop here. Let us discuss about recurrent neural network in the next class. Saturday we'll have quiz 3. Okay. So yeah, the time is less. So hereafter probably I think every week we'll have one quiz or test, because by this month end we have to pack off everything, right? So whatever we have discussed after test 1 until today, what we have discussed till that point, we'll have quiz 3 on Saturday.